All right. So I just changed one of the examples. So remember, all of these examples end up attached to the website eventually. I just changed this one to make it as compact as possible. So primary key constraints, stick them on the same line as the attribute definition. Similarly with branch name, put the foreign key declaration where you don't need to say foreign key, I don't think. Here, so you can just say that that references that, or maybe I could even get rid of that. I could just say references branches because the attributes have the same name. Another thing about, so I tend to write uppercase letters at the start of table names and lowercase letters at the start of attribute names, and I use camel case. That's a little bit weird when you're looking at the information in Postgres, because the uppercase goes away and you end up with things that look a bit unusual. So, so potentially you could use underscores there as well. Do all the entire attribute names using underscores, and then they'll look the same when you're looking at them in Postgres as they do when you're editing the file. And one final thing about this, in the held by table, I can certainly specify that these two attributes are foreign keys, and I can do that in the attribute declaration itself. It wouldn't make sense to say account text primary key references that and customer integer primary key references that, because it's actually the combination of these two things that forms the primary key. So if I stick the primary key declaration here, it's kind of implying that that attribute is the primary key. So if I was to try and stick primary key here, it would end up having two primary keys. All right. Now the next exercise was a continuation of that one to try and be a little more precise. So rather than just using text and integer for the values, try and capture these ideas. Now I've already done that, and since it's taken so long to type stuff in, I'll just go straight to the declarations. Okay, if you know about regular expressions, that's just a regular expression that means 7 digits. Tilde is the regular expression matching operator in Postgres. What I've done here is effectively I've given a name to a special type, which is, this is kind of like a type def in C, where I say, all right, this type is 7 chars, which is true. It's always going to be 7 characters long, and then I want to check the value, and that's how I do that. So the value that I'm storing in an attribute which has this type is a 7-character string which consists of 7 digits. So that'll do that for me. Now where did that end up? Oh, that was customer number type. So I use that down here. Okay. So the customer number is of type cust number. Now there's a number of other ways I could do this. I could say that customer number, spell out the type declaration here rather than use the named type. Obviously it's smarter to use the named type, but that's exactly the same declaration as we had above, except that above we use the keyword value. Here we have to use the attribute name. Okay. So this check syntax introduces an additional constraint on top of the basic data type constraint. So how do I define customer number? Well, I could say it's a 7-character string where all of the characters are digits. Another way I could define it is I could make it an integer, and then I could typecast the integer into a 7-character string, and then also do the same check that it's 7 digits. That character string is 7 digits. And the other way, I guess, if you don't care about leading zeros, is I could say that the customer number is an integer and it has to be in this range here, which is the range of 7-digit integers. So all of these declaration types are possible for the customer number. What else? Branch, well, there's not much I can do about that. I mean, I can make them varchars and things like that. For an account number, we know what account numbers look like. We know they look like this. So we can write a regular expression that will capture that. So that's the guts of the regular expression. It's an uppercase letter followed by a hyphen followed by 3 digits. Now, the reason I've had to put this additional stuff here is that I've defined this as type text. I could define it as type char 5, and then I wouldn't need this and this. So basically what these are doing is saying at the start of the string I've got a single uppercase letter, and the last 3 characters in the string before the end of the string are the 3 digits. So an alternative rendition of that declaration, where am I? Would be to say char 5, and then having done that, I wouldn't need those. So it's really, I mean, it's up to you to some extent how you decide to define it. But you've got scope for doing it. And of course, I can take, I can define an account number type if I wanted to, in the same way that I defined a customer type up here. The other thing I wanted to say is the order of these things doesn't matter, because you pretty much refer to them by name. So it's kind of like a struct in C. Doesn't matter what order you write the fields in C, because you're not referencing them by a position in the tuple, you're referencing them by that name. Integer, or I've said we're not allowing overdrawing. This constraint here is also something that we can't implement. Sorry, the first one we can do. We can insist that all branches have at least $10,000, and we can do that by adding a declaration here. Is that 10 or it's 100? So I could do that if I wanted to enforce that constraint. This constraint is a little bit trickier. It's basically a cross-table kind of constraint. So the balances I'm getting are coming from the accounts table, and here I'm trying to use that information to enforce a constraint. Oh, in the accounts table, sorry, they're coming from, where are they coming from? Big balance check. Oh, maybe I can do this. Big balance check, Oh yeah, I was thinking of assets. So I can't enforce that the assets in the branch is equal to the sum of the balances in the accounts. I can't actually write that as a constraint. However, there are other ways that I can enforce the database will do the right thing to maintain that asset value correctly. In these check constraints, you can also refer to other attributes in the table. So where have I got a table that's got 2 integers? Probably don't. Now, if I had a table that had 2 integers, x and y, I could insist that x was greater than y, and that would also that would work. Another thing I've done here, notice that I've insisted that the value of a customer address, that's a little bit weird. It would make a lot more sense if this constraint was applied to a branch address. Have I done that? No, I haven't. Aha. So that declaration I had down the bottom is mighty odd. You probably wouldn't do that. So what that would mean is that you couldn't have more than one customer. Oh, sorry, that's the customer address. Yeah, or it's still a bit odd. You couldn't have more than one customer living at the same address. That may be true, but it seems a little bit unlikely. Might be more plausible to say you can't have two branches at the same address, which is what that would enforce. Notice that we can be explicit about something being unique. It's implied if you define something as a primary key, so there's a unique declaration forced by that. And similarly, a primary key isn't allowed to be null. So effectively, when you define something as a primary key, you end up with those two constraints being added to the attribute. So I have to specify an address. I can't just say, I don't know what the address is, and the address has to be unique. In other words, we can't have two branches at the same place. Any questions on that? I think I introduced a lot of additional stuff on that slide. For all of this stuff, go and have a look at the Postgres manual to find out. I mean, there's a hell of a lot more that you can do than I've shown here. Notice, and reminder, all of these double hyphen things, they're comments. They're not part of the declaration. Is there anything else interesting there? Oh yeah, there it was. Oh, actually that's a good point. If you want to have a constraint that cuts across multiple attributes, you have to specify the constraint after you've defined all the attributes. So in this table with two integer values, I can say that I want the first integer value to always be larger than the second. Therefore, I wouldn't be able to insert a tuple into that table where x was 2 and y was 3. Okay? So here I'm being explicit about the constraint. In the others, there are constraints hidden in the primary key. There are constraints hidden in the foreign key. And if I want to specify a constraint on a particular attribute, rather than using the word constraint, I use the word check. Alright, that's a lot of extra notation to chuck in. I'd say it can take quite a bit of effort to specify all of these constraints. And as I said, this one you can't do with a constraint in SQL data definition language. Alright, so hopefully that's enough that you could write an SQL declaration to represent a particular relational schema. So now what we're interested in is taking a look at how we convert ER diagrams into SQL schemas. So since ER modelling gives you quite a nice representation of your data model, it's probably useful to do an ER model anyway. The other thing about ER models is that they lead to database to relational schemas that avoid some problems that we'll look at later in the course. Once you've got your ER model, you then transform it into a relational model. So the mapping that I'm going to show just tells you how to take an attribute and convert it into an attribute in the table, how to take an entity, convert that to a table, how to take a relationship and convert that to a table. And you can specify the names of the attributes, but the additional stuff that you have to supply is all the domain information for the attributes. And similarly, other types of constraints, like you don't want the attribute to be null. That's not specified at all in the ER diagram, except implicitly if you've got a key attribute, one of the ones that's underlined, so there's an implicit not null and unique there, which you'd render in the in SQL as a primary key declaration. Alright, so there are some correspondences between the relational model and an ER model, that an attribute in ER maps naturally to an attribute in the relational model. An entity maps to a tuple. An entity set, basically, and remember that I've been using this terminology and it's sloppy. A lot of the time I talk about entities, but what I really mean is an entity set. But an entity set corresponds to a relation in the relational model, and a relationship may correspond to a new relation in the relational model, but it might also correspond to a foreign key in one of the tables in the relational model. What have we got here? Oh yeah, the relational model doesn't have composite attributes and it doesn't have multi-valued attributes, so we need to think of some way to represent those kind of constructs in the relational model. And the relational model doesn't have any notion of subclasses, so we need a way of mapping subclass hierarchies to the relational model. Right, so let's start with something simple. An entity that doesn't have anything else unusual about it just becomes a table. And the entity has a primary key. That primary key carries over to the table. So given this ER diagram, it's pretty easy to write create table student, stu ID, integer primary key, if you want to write it like that, name text, degree text, or maybe integer if we're talking degree numbers like 3707, and your table's done. Okay? So there's your table. Weak entities are a little bit different. So here's a weak entity, and I've slightly changed the notation so the discriminant attribute in the weak entity is written like that. I think in the other examples I had a dotted underline on name. But that's kind of a half-baked key. It's not a proper key until you combine it with the primary key for the strong entity table that this weak entity is associated with. So you can see from this diagram, every contact must be related to an employee and related to a single employee. I guess that's interesting if you've got two people working at the organisation and they both have the same contact. That cannot be represented under this model. Okay, you'd have to change the definition a little bit. You'd have to get rid of that arrow essentially. Alright, but the way you represent it in the relational model, this strong entity is pretty straightforward. So we just take all of the attributes, make them attributes of the table that represents the entity set, and the primary key is unchanged. The difference is in the contact table. So the weak entity can't exist by itself because name isn't a primary key. So we have to add the social security number of the employee to which they are related to the table that represents the contact weak entity. So basically, kind of what I was saying before about weak entities, they don't become, or they don't have a proper key unless you include the primary key from the entity that they're associated with. So putting those two attributes there gives this weak entity a primary key. So there was kind of a relationship involved there. So let's have a look at general relationships. So we've got a customer who may own one or more accounts, or 0 or more accounts, and an account may be owned by 0 or more customers. Right, so the representation of the customer is pretty much as we've seen before. Same primary key carries over to the relation that's used to represent the customer entity set. Similarly with accounts, so we've got those 3 attributes as part of the accounts table. And then finally, the relationship becomes represented by a separate relation. Okay. So basically, if you look at what's going on with a relationship like this, it obviously involves each relationship object involves a customer, a particular customer, and a particular account. So you basically take them, stick them in the table. It's kind of like the held by table that we had before. And any attributes that are associated with the relationship also go into that particular relation. So mapping end-to-end relationships is pretty easy. Notice here I haven't got any participation constraints. Representing them precisely in SQL is a little bit trickier, as we'll see. Alright, a one-to-end relationship. We kind of saw an example like that with the weak entity model. So if we've got a customer and the customer must be associated to a branch, then we may as well put a foreign key for that one branch into the customer table. So that's what we've done there. So the relationship has ended up being represented by an attribute in one of the other tables. Now additionally, we've got some other information about the relationship, like when they joined that branch. That also goes to the customer table by virtue of it being an attribute on the relationship, the one-to-one relationship. So effectively, those two things there represent that. In this relational version, you can't see the additional mechanisms that are required to implement the total participation, but we'll have a look at that in an example in a minute. A branch doesn't need to be linked back to the customer. It's not associated with a single customer, so we can set up the linkage between a customer and a branch via the customer table. So we don't need any additional stuff in the branch table. So that's a pretty straightforward mapping of that part of the ER diagram. Any questions on it?
Yeah, what if there's no error customers, it's some customers?
Sorry?
What if just some customers, no error customers, the relationship?
So you're saying...
So if it's just some customer, no error customer, so how do we represent the relationship?
I don't think the relationship would change, but the definition in SQL might change. So this simple box, and I didn't bother doing the arrows in this because they're a pain to draw. So anything in this orangey colour is a primary key, anything in the green colour is a foreign key. Okay. Right, it might answer your question when we look at some more examples. Alright, so here's an example of a customer and a home branch. Ah, no, ha ha ha. All right, this is interesting. So we saw we could represent end-to-end relationships by representing the relationship as a separate table. Okay? So that's what we've done here. Are there any problems with doing that? You can certainly have the fact that John has home branch Coogee by saying John Coogee and whenever joined. So you can certainly represent the fact that a customer has a home branch, but if this is done as a separate table, you can't prevent the same customer appearing more than once. So you wouldn't be accurately representing this where a customer can only have one home branch. So if I use this representation, I could say John has a home branch in Coogee, but then I could also say John has a home branch in Marrickville, or something like that. Okay. So it, if you like, implements something more general than what the diagram shows. So you need to go back to, oh, I went forward, I need to go back. So this example here completely represents, or accurately represents, what's in the ER diagram, and the SQL representation would need to say that the branch number inside the customer is not known. Okay, so a customer has to have a home branch, so you simply add the additional constraint that the foreign key from branch number that refers to the branch table is not allowed to be null. So that's forcing the customer to have a home branch. The fact that you can only fit one branch into here means that the customer can only have one branch, one home branch. But this representation here allows the customer to have multiple home branches, which isn't what the diagram says. So we wouldn't use that as a representation for that diagram. Is that subtle difference clear? One person nodded. It's always a sign, but it might only be one person who understands. Right, let's have a look at this. So convert this to relational form. So we've got a customer who has a favourite store, who may have a favourite store because we don't have total participation here. So the customer doesn't necessarily have to have a favourite store, but a customer must have at least one account, and an account must be owned by at least one customer. An account, so here we're talking about things like David Jones cards, which probably no longer exist, but they were tied to a particular store. So the account is associated with one store, and a store may not have any accounts associated with it, which, okay, that's what we want. Well, that's what the diagram tells us we want. All right. How to represent this? Well, clearly these relationships here don't have to exist as separate tables. So we can have, in the customer, we can have an attribute, which is a foreign key referring to the store table, and that will represent that because we know the customer is only associated with one store. Similarly, the accounts table can have an attribute which is a foreign key referencing the store table as well. And that'll represent the attribute that the account is the store that the account is associated with. This relationship here is an end-to-end relationship, so that requires us to have a separate table where we can have multiple instances of customer for several accounts, and similarly a single account could appear multiple times in this table associated with several customers. Alright, so let's have a quick look at the SQL exercise 3. So to save a bit of typing, I've done that. Alright, so one table is account. Actually, that's not a good one to put first. Probably the best one to put there is store. So we know for sure that we've got these three entities in the database. We have to store information about stores, customers and accounts. Right, so what do we know about stores? We know that stores have a phone number which is unique and an address. Phone. And the primary key is the phone attribute. Of course, we can't say its domain is domain. We have to give a particular data type. That can be text, and for the phone, let's be lazy and make that text as well. So that's the representation for a store. What about an account? Alright, an account has an account number and a balance. Notice I've put a hash here for the account number. Some databases, i.e. Oracle, allow you to use hashes in field names or attribute names. Postgres doesn't, so we have to change that to something like account number. Something like that. And let's, for the sake of having something different, let's make that an integer. And what else did the account have? It had a balance. Well, it's a bit different than a float. So that's a dollar value associated with. Actually, let's just see. It might help if I said currency. No. Obviously not recognised as a standard SQL type. So we'll leave it as a float. The primary key is the account number. Customer has customer number, name and address. So that's also an integer. Alright, so we've done the basic information for the entities, but we haven't captured the one-to-n attribute. So an account must be associated with a store. Okay. So we've got an account. The other thing to notice is that the type here has to correspond to the type there, because the value that we're getting here should be something that we can find in the other table. So the store, the text, the references. So we're storing the store phone as the foreign key. Have we completely captured that relationship? No, we haven't, because there has to be a foreign key value. It can't be null. So we need to add an additional piece of information. That the store value can't be null and it's a foreign key that references the store table. On the other hand, for customer, we've got a customer has a favourite store. There's no total participation there, so we can have a foreign key that references store, but it doesn't have to be not null. So that would work for that. Notice I've used store as the name. I haven't really captured the semantics of what that relationship is all about. So maybe changing the name to something that captured the notion of it being something favourite might be useful. So I could call it that. Doesn't matter what I call it here, as long as I point out that it's related to that attribute there. And the final thing is customer has an account. All right, so that's an end-to-end relationship. Using the name has as a table name is a bit sus. I'm sure there's a reserved word has somewhere in data in PostgreSQL. And this is an association between a customer and it's a reference to the customer table and the cust number attribute in that table. That's a reference to the account table. Oh no, and I didn't follow my own convention of calling everything plural. So I really should have had accounts, customers, and stores. Never mind. I've gone this far. Alright. Final thing, we need to say that customer account forms a primary key for that table. Okay. Now, getting back to the point someone made before, one thing we haven't captured is that a customer must have at least one account and an account must have at least one owner. And given the way we've described this, we can't actually enforce that constraint. And so we're missing something in the SQL schema that was implied by the ER model. And the primary key isn't going to save us. These two things have to be null, have to be not null because they're part of the primary key. But we don't have to have any entry in the has table that refers to customer John, whereas it would suggest that any customer must have an account. Okay? So, as I said, we've lost some of the semantics going there. We'll see ways later that we can try and bring something of that back into the definition. Mapping one-to-one relationships. Okay, we've got narrow at either end. So here we've got a manager who manages a single branch, and a branch has, and a branch may have a manager. So a manager has to have a branch might have a manager. Right, so this is how we've decided to implement that. Still got 2 minutes before Echo cuts off. So the implementation here, we've got an arrow at either end. So in theory, we could put the manager as part of the branch, or we could put the branch as part of the manager. Okay, either way will allow us to represent that. So what we've done, we put the branch as part of the manager, and one reason for doing that is that every manager has to be involved with a branch. So every one of these entries is going to be not null. If we put the manager here, with the manager's employee number, some branches don't have managers, so that attribute would have a null value. Okay? So potentially we're wasting some space for attributes by doing that. Talk more about that next time. Okay, let's go.